you're going to count towards this new school? Are they
Um,
going to transfer?
yeah, they're going to transfer him in. Yeah, so he'll transfer into the new school, and then we looked at their math program. We just go right in down for two down there. Big school, 1,200 kids, I guess. Relatively big compared to here, small compared to others. But guys, I don't know how quickly they'll get there. Probably 4 days. I think it's, yeah, 3.5, 4 to get to Montana. I think when we did it from Colorado, that was like 5.
It's like 8 or 9 from Florida.
You drove from Florida to here?
Yeah.
When?
When we moved up here.
Oh, when you moved.
So like 2010, I think.
8
8.
days.
Yeah.
So did you go through Chicago?
I don't think so.
Probably not St. Louis.
Yeah, I remember going through not Montana, Wyoming. That was like the previous place.
Yeah, first few years that we lived here, we thought it was really cool to drive back and forth every summer.
Oh.
We did it 3 times. And then after the third, was it 3 times, or did we do it twice? I can't remember. After the last time that we did it, I just, like, it got pretty seedy somewhere between Fort St. John and turning down to Skagway. And it's like, we're not getting along very well. We're not going to do this again. It was not pretty. And so now we just fly down there and rent a car and keep the car the whole time and then fly out of a different city. So easy. Go fly to Tennessee, drive to Wisconsin, and fly out from there.
Do you have family in Tennessee?
Joan's dad lives there.
Oh.
And she has cousins and stuff.
Oh, right. Did she go there? Did she go to Tennessee? Like, the university?
Well, during the summer, she's done stuff at the Tennessee State, but no. Most of her university stuff was at Boulder and at River Falls. But,
I thought she had like a Tennessee shirt.
yeah, she does.
Okay.
But she didn't go to the University of Tennessee.
Okay.
That was Middle Tennessee State, which is Murfreesboro, which is outside of Nashville. But she did a lot of her work at the University of Wisconsin-Milwaukee as well. So, anyway, we've got to do this. We only have 40 minutes. We don't have that anymore. The weight of a body above the surface of the Earth. Okay, so it varies inversely as the square of the distance. So, in terms of y is equal to k over x, now that would be to the n. When they say inversely as the square of the distance, we've got to put the distance squared down here. So the weight varies inversely as the square of the distance. That's how you read and write that stuff. Weight varies inversely creates this. And then as the is what x becomes. So in this case here, if the astronaut is 300 miles above, we need to find the distance. So for part B, when the astronaut is 300 miles above the Earth, we have to add that 4,000 miles, which is the approximate radius of the Earth. So 300 miles above is going to be 4,300 miles. And then for part C, it says, just suppose an astronaut is 170 pounds on the surface. What do they weigh in orbit 300 miles above? So they only give us 2 numbers there, but we should, from the drawing and the introduction, know the third number that we need. You see, what we're trying to do is have both a weight and a distance to find k. Once we know k, then by either knowing the weight or the distance, we can find the other. So, his weight on the surface of the Earth, or her weight, is 170. And if we're going to find k, we need to know that distance squared. And the distance, when they're on the surface of the Earth, is 4,000. So there's 4,000 squared. Now, k is going to be equal to 4,000 squared multiplied by 170. I'm not worried what that number is yet, because we can just write it into solving for the weight above the surface of the Earth. So above the surface of the Earth, 300 miles is this distance from the center. So what we do is we take this K value, we plug it back in here, and then we use this number as our distance squared. So now the weight becomes the K divided by the distance squared. So if you do all of that, watch this. So now it's 170 times 40 times 40 divided by 43 times 43. You can do that a little faster. That's why I say save writing all of these intermediate values until the very, very end. So that's what the weight is. It looks like it's going to be, so this fraction here, this 40 times 40 over 43 times 43, is a little bit less than 1, so that means that person's going to be lighter, which makes sense. You go up, you get lighter. What is it? 147. Okay. So there's the K value. So now you can use that for anything. Here, let's say you weighed 110 pounds. If you take, wait, no, other way around. I don't want to do that. Let's see. If you did 4,000, oh, you got to turn this into miles. Rapinski is almost a mile high. So there we go. And now if you take your weight if you do that arithmetic, you can figure out what you weigh on top of Rapinski if you start out down here at 110 pounds. What is it? Want me to do it? And then we come up with it. So this would be, if you put 110 in here, and then multiply it by, oh, you have to square that thing. So, gosh, 110 times 4,000 squared is divided by 4,001 squared is, you would weigh 109.94 pounds. Hardly any difference. Would you weigh less? Yes. Is it measurable? No. So you got to go to space to feel it. So look up to Rapinski and say, "Oh, I feel so light."
What about like non-numbers?
Well, you know, if 4,000 or 5,000 feet got ourselves less than a tenth of a pound. If you do 6 times that, maybe we'll get ourselves up to, a pound less, because it's not linear. Yeah, okay, 17. At 7 feet 7 inches and 303 pounds, Jorge Muresan, who is one of the tallest people ever to play professional basketball. For people with similar body shapes, weight varies directly with the cube of height. How much would you expect someone with his body shape to weigh if they were 5'10"? So if you turn that 7'7" into all inches, I think it would be real easy to work with. So you take 7'7" and turn it into inches. That's how many inches? 91 inches. And it's 300 and, how much? 303 pounds. And then we have somebody who is how tall? 5'10"?
Yeah.
So what's 5 feet 10 inches? 70 inches, and we want to know this. And it varies directly as the cube of weight or height? How does that go? Height. So weight, is that what it says? Weight varies directly?
So it's not that.
It's not that one, it's this one. Weight varies directly as the cube of height, so that's like this. So now if we change our variables, so we use weight and height, W and H, weight varies directly as the height is cubed. So you take these two numbers right here and plug them in to figure out K. Divide. So this is K. And then you use that K value with 70 inches to find the weight. So we then say, well, our weight is equal to this K value. Is that okay?
Yeah.
Times the height, which is 70 to the third power. And you do the arithmetic, you'll get the weight. So 21A, at a certain time of day, a 13-foot tree casts a shadow 7 feet long. Draw a picture of the situation and mark a right triangle in the picture. So hopefully you didn't go and turn this into a masterpiece drawing. Tree, shadow. Okay? Is that good enough? That's my tree, that's my shadow. It's 13 and 7. And that's a right triangle. A nearby tree is 18. How long would you expect the shadow to be at the same time of day? So these are a one-to-one relationship. They vary directly. Nothing squared. It's just a direct variation. So if it's a direct variation, we can go and say, there's your shadow line. You can say that 13 over 7 is going to be the same as 18 over 5. Because these are similar figures. 18 over S. So then 13S is equal to 18 times 7 divided by 13 again. There it is. So we're talking similar figures. You know, here's your 18, and then whatever that shadow is going to be. It's going to be a little bit longer. Is that okay? Enough explanation? All right. Titular. So are we on at 9:05?
Yes.
Yeah, I don't know if we're going to get the whole 2-3 introduced or not. Well, let's take a look at it. You have your calculator. We're going to need a calculator. We're going to need a sharp pencil and a lot of paper for this one. The whole set of this activity here, it lays out a lot. And it's a long process to go through all of this. There's a bunch of relationships that get put together. But the fundamental theorem of variation is essentially working with direct and inverse variation and being able to apply, make an application of these things. And then what we've done is we've said, well, here's one height and weight, for example. Let's find another height and weight combination. Well, what we're going to do with this activity here is we're going to look at volumes and radii of round objects, lollipops of all things. And we're going to look at how their volume and their radius compare. And then we're going to take a look at how we can package them and put them into boxes. So this is like an engineering type of problem. And there are people called industrial engineers that deal with this stuff every day. You know, why is a soda can shaped the way it is? Why is a beer can the height that it is and the width it is? A lot of people say, well, it's because that's the size that fits into the hand, for example. But it's not necessarily that way. It has to do with packaging and shipping costs. Back in the day, before plastics were so widely used, oil for vehicles. A quart of oil did not come in a plastic bottle that was that semi-rectangular shape. It came in a round can. And that round can had metal top and bottom, and then it had waxed paper as the side of the can. But an oil can was not a comfortable size to grab with your hand. It was a little bit too big, and then when the thing was all oily, and then your hand would slip on it, they were a freaking mess. So you had to be careful with them. But there was a reason for the size. You know, why didn't they make them taller and narrower so it'd be easier to hold on to the can when you're putting oil into a vehicle or something, changing oil? Well, the oil companies, they knew it had to be a cylinder. And what they did is they made it so that the construction of the cylinder would use the least possible material for holding a quart of oil. And that was what an oil can was shaped like. It had nothing to do with convenience. It was minimize the cost of the packaging. And if you look at stuff in stores, packaging in many cases is a significant part of the cost. So whenever they can minimize packaging, that's a good thing. You know, all these energy drinks that are tall and narrow and stuff like that, it's extremely inefficient. You're paying a lot for the packaging with those things. That's part of why they're so darn expensive compared to other things. Whereas you look at something like a 2-liter bottle of soda, crying out loud, these things are dirt cheap for how much you get compared to a can. Well, it's all about packaging. You have lots and lots of volume inside a lesser ratio of surface. So this problem here is of that nature. It's probably really the first one that you're ever seeing in math that goes down this pathway. So it says, I'm going to read right through this with you, and we're going to crunch numbers. It says, Fruit Roll Industries makes mini and regular fruit pops and is considering making larger jumbo pops. We assume the production cost, which is P, of a fruit pop varies directly with the volume. So if you have more volume, it costs more. Makes sense. More sugar, more color, whatever you have to put into it. So it varies directly with the volume. So then P is equal to K times V. I'm going to make note of that. And I think they use K sub 0 in the writing. That's K naught is how we read that. Naught is a short way of saying 0, and it means the beginning. So that's K naught. And so then we assume that the pop is approximately a sphere. So that means the volume is equal to 4/3 pi r cubed, because that's the volume of a sphere. So let's keep that in mind. Volume of a sphere is 4/3 pi r cubed. So r is the mean radius, or the average radius. So then, as a result of that, what we do is we take that volume and we substitute it up into this direct variation. So now, this goes and gets plugged in here. So we rewrite the direct variation, which is going to be K times 4/3 pi r cubed. So then they say, since 4/3 pi and K are all constants, in other words, they don't change, 4/3 pi K is the constant, and we can write K r cubed. So these all are constant. See, 4/3 and pi is going to be the same all the time. So we can incorporate that into our K value. So if we write it, we can say P is equal to K times r cubed. And then we'll figure out what K is altogether. So P varies directly with the cube of the radius. So the production cost, you think, does it make sense that the only thing that's changing here is the radius of the lollipop? So the production cost is going to vary based upon how big the radius is. The bigger the radius, the more it costs, because you have a bigger volume. And the 4/3 pi, then that's constant, that becomes a part of K. So there's your volume relationship compared to the production costs. So what they would like us to do is they would like us to put together this table. This thing generally takes, we're not gonna get this done, but we're gonna see how far we get with it today. Okay, so this size is gonna be named mini, regular, and jumbo. And the radius cubed is going to be measured in cubic centimeters. Oops, I'm sorry, I'm going too fast. We need something before that. We need to say what the radius is. So the radius they give us for size is 7/10, 1.4, 2.1. So now we have to find the radius cubed. This is all in centimeters. Maybe just keep that in the back of our mind. So they give us 7/10 cubed is 343 thousandths. What's 1.4 cubed? You want me to do numbers for you? .744, 2.1 cubed, 9.261. So then we need a ratio of the radius to the mini's radius. So a ratio of the radius to the mini's radius. So this to itself is going to be a 1-to-1 ratio. This to the mini is what ratio? I'll slow down. Try to slow down. National Lollipop Day is July 20th. It is. But we can simplify that. So let's go here. Are we ready to look at these ratios? You two are? Are you ready to look at ratios? Okay, so the mini to itself is going to be a 1-to-1. It could be 0.7 to 0.7. You said that the regular would be 1.4 to 0.7, and that would be simplified to be what? Well, if it's 1.4 to 0.7, that's like 14 to 7, which is 2 to 1. So it's twice the radius. Okay, what about the jumbo to the mini? That's a 3 to 1, because there's 21 and there's 7. So it's a 3 to 1 ratio. Convenient numbers, yes? So the ratio of the r cubed to the mini's r cubed. So that's essentially, that's the volume now. So they tell us it's a 1-to-1, of course, for the first, because it's the same size, yeah? But what about now, here's r cubed. What about this number to this? What's that ratio? What is it? Okay, so now, can you just do this in your head? I don't know how you've been exposed to it, but I know how they've been exposed to it, because I've been teaching them math since they were in 6th grade, right? 6th grade, 7th grade. Patty had you guys for a while, that's right. 7th grade though. So this is only our 4th year, 5th year together. So, but I know what they've had. We did this in 8th grade. Here, let me show you guys this one. Let's do it with cubes. If I have a cube which measures 1 by 1 by 1, and then I come along and I triple each dimension, so now I make it 3 times as wide, and I make it 3 times as tall, because I'm working with volume. And then I make it 3 times as deep. What did we do to the volume of this original cube here? By making it 3 times as wide, 3 times as tall, and 3 times as deep. What happened? The volume of this cube here is 1. What's the volume of the new big cube? 3 times 3 times 3, which is 27. So we started with a 1 by 1 by 1, and then we turned it into a 3 by 3 by 3. So this is 1 cubed, this is 3 cubed. So the dimension changed, and whatever the change was gets cubed for volume, whether it's a cube or a sphere, because of that third power. So now instead of this thing being this big, we made it how many times bigger? Twice as big. So this number must be twice, twice, twice. 2 times 2 times 2. So from here to here must be 8. Do the division. 2.744 divided by 3.43. What do you get? That's 8. Did you get it? That's 8. So it's an 8 to 1. So we don't have to do the calculation for the last one. How many times bigger is this one in a radius? 3. So 3 times 3 times 3, so this is 27. So it's 27 times the volume. And the regular is 8 times the volume. So, even though you just made it a little bit bigger, the volume just went whoosh, because we did it in all 3 directions. It's not like making a pancake thicker. It's making a ball bigger around. So basketball versus a ping pong ball is a dramatic change. Ping pong versus tennis ball, dramatic change, I guess, would be more realistic. So if the production cost is a half a cent, right here, what's it going to cost to produce the regular size? If it's directly proportional. So production cost is directly proportional to the volume. So in other words, if the volume doubles, the production cost doubles. If volume goes up 10 times, then the production cost has to go up 10 times as much because you're using 10 times as much material. Yeah, so this is the one that has to do with volume. So if this costs a half a cent to produce, that thing, this is 8 times as big. What does that cost to produce? 4 cents. And what does this cost to produce? A large one, the jumbo. $13.50. 27 times as much. Because your volume goes up 27-fold. It's 20 times as much volume, so it's 27 times as much sugar and color and whatever else. Okay. So add super jumbo, which has a radius of 2.8. Add that in here. So a super. They're making a new size. That's what they do. And they say, put in the rest of the numbers, go. Yeah, why not? Huh? What, 28 divided by 0.7?
Mm-hmm.
Yeah. So what did you get for a volume, Nick?
1.95K.
Okay. So then the radius of this to that is 4 to 1, 28 to 7. So now the ratio of that number to that number, we ought to be able to just calculate, because we made the radius 4 times bigger. So it'd be 4 times 4 times 4, which is 64 to 1. So now it's going to cost 64 times as much money to make it. So that's a 32 center. So that's why those really big lollipops that you see, it's like, geez, that's really expensive. It is. There's a lot of stuff there. So then the next part of this whole thing is fitting these into boxes. They only have one size box, so they gotta put little ones in or bigger ones. Clearly, the bigger ones, you won't get as many in, right? But there's a whole nother engineering marvel there. Is can you come up with a particular box size that is gonna fit all of them so that they fit in tightly? And yeah, that can be done, but that's not part of our game. So this is the direct variation portion of this activity. The next one is going to be the inverse. And the inverse is going to be step 4. And then there's a generalization that happens in step 5. So here's what I'm going to do. I'm going to send you out of here with trying step 4 on your own. You know, they say, there's one size carton. As the radius of the fruit pop gets larger, what happens to the number of pops that would fit into the carton? So as you have a bigger and bigger radius, what happens to the count of what goes into the box? Bigger pops, you can put more of them in?
Oh, there's bigger box.
No. As the radius of the pops get bigger, as the radius of the lollipop gets bigger, and the box size stays the same, what happens to how many lollipops fit into the box? That becomes less, and that's an inverse relationship. So what they give us is that the number is equal to k divided by r cubed. And they have a new table for you to fill out, which will give us the number of lollipops that fit into a carton. So why don't you try your best to have that done by Monday? Tuesday, what am I saying? Tuesday. And then when you come back, we'll finish the introduction to this thing, and you'll have a bunch of time to work on problems in class, because it's an hour-long class. So I'll change what's on the website in terms of our pace and our homework and what have you.